Hey everybody, Mr. Tannen here for this proof of the chain rule. So we're going to actually use for this proof the our definition of the derivative, the limit definition. So if we recall our limit definition, uh, we know f prime of a is going to be equal to, this is one of our definitions, but as b approaches a, of f of b minus f of a all over b minus a. Well, this is a different definition than we often think of initially, because sometimes we have the differential approaching zero. But if you think about it, it's the same thing if the two values are approaching one another in this limit, as the differential being approaching zero. So now, if y were to be in the format, the function we're dealing with were to be in the format that we've been noticing we need to use the chain rule with, then how would we input this into our derivative definition here? So, well, my derivative, according to this definition, would be the limit as h approaches 0 of f of g of x plus h, because this is my function within a function, and then this would just be f of g of x all over h. So we're using our original definition, and you'll see why we're going to reconsider this in a moment, times the derivative of the interior oops yeah. Well, what you notice here is what I'm just taking the step structurally to help with this proof is I'm just going to multiply this by the difference of g of x plus h minus g of x over itself. So it's not changing the value of this. It's just going to give me something here that will allow me to simplify. So bringing down my limit notation here, well, what I could call this g of x plus h, if I revisit that original alternative definition of the derivative we used, well, we could think of this here as b and this as a, right? And then in the denominator also, that's going to be the same case, where we would have, now that I'm multiplying this over, g of x plus h minus g of x. Well, what I'm able to do is switch these out, and what you're going to notice here is, maybe in a second, how we're approaching our chain rule, is I've just swapped this h and this other denominator, and what you notice is I ended up over here is quite simply just the definition of the derivative of the g of x function. But looky here, well, if I were to again identify this, this is just b and this is just a. So we can see that as h approaches 0, this left side is actually the same thing as the derivative, right? So this is the same thing as h approaches 0 of b approaching a. And this b approaching a, as we can see, is the exact definition that we had written above. So for the purpose of this proof, we revisited that because now we know that as h approaches 0, we can formalize this here in writing, that this is approaching this. So what we had labeled as B approaches A. And now we can see that this is just, let me switch my colors here, f prime of g of x. That's what this derivative is, times, well, what is this? That's just the derivative of the interior function. So we were able to show then in this proof, this is specifically what our chain rule is, as we saw up here, I believe, in this elvish meme we had. Uh-oh. Okay, here we go. Or as we had, I think, written it, we had it written right here, right? We can see that what we end up with is precisely the chain rule. So we were able to, taking this alternative definition and thinking of it as one of value approaching the other, we could then see that just by taking this organizational step of multiplying them by something over itself, it allows us to show by just some simple mathematical steps, algebraic steps, that we simply just have the derivative of f in terms of the interior function times the derivative of the interior function, which, as we saw, as Nancy Pi also shared up here, the derivative of the outside function leaving the inside alone times the derivative of the inside function. Hope this proof was enlightening and you're able to see how the chain rule can actually be derived using the definitions of the derivative we've already worked with. Much love, everybody. Have a nice day.